Episode 12, Breaking the Limits, Paging and Segmentation. Welcome back. In the previous lesson, we ended with a tough problem of contiguous memory allocation, fragmentation, especially external fragmentation, which wastes precious memory resources. To completely solve this issue, operating system designers came up with a revolutionary idea. Why must a process reside in one single contiguous block of memory? Today's lesson dives into two non-contiguous memory allocation techniques. Foundations of modern systems, paging and segmentation. Part 1. Paging, the dominant technique. Paging is a memory management method that allows the physical address space of a process to be non-contiguous. This technique is used in most modern operating systems. 1.1. Basic concept. The logical address space of a process is divided into fixed-size blocks called pages. Physical memory RAM is also divided into fixed-size blocks called frames. Page size equals frame size, for example, 4 kilobytes. When a process is executed, its pages are loaded into any available frames in physical memory. These frames do not need to be adjacent. Analogy: you have a long document process and a notebook with scattered blank pages physical memory. Instead of finding a consecutive sequence of blank pages, you tear the document into separate pages and paste them into any blank page of the notebook. To keep track, you need an index that tells where each page of the document is placed. 1.2. Address translation mechanism, the index in the OS is the page table. Each process has its own page table. A logical address is split in two. Page number P, used as an index into the page table. Offset D, relative position within the page. Translation steps. 1. CPU generates logical address P, D. 2. MMU uses P to look up the page table entry and find the corresponding frame number F. 3. Final physical address equals FD. This removes external fragmentation completely. Any free frame can be used. However, internal fragmentation may occur in the last page if the process size is not a multiple of page size. 1.3. Performance issue and TLB solution * page tables are stored in main memory. Thus, each memory access requires two memory operations. 1. Read page table entry. 2. Access the actual physical memory cell. This has system performance. Solution: translation look-aside buffer TLB, a small, very fast cache that stores recent page number, frame number pairs. Translation steps with TLB. 1. CPU generates PD. 2. MMU checks TLB. TLB hit, frame F found immediately, very fast. TLB miss. MMU accesses page table, fetches F, and stores PF into TLB due to locality of reference. Programs repeatedly access a small set of pages. Hence, TLB hit rates are usually 99%, making the performance overhead negligible. Part 2. Segmentation. A logical view note 131 to 140. Segmentation is another memory management technique that views the address space as programmers perceive it. 2.1. Basic concept. Instead of dividing programs into equal-sized blocks, segmentation divides the logical address space into variable-sized blocks, called segments. Each segment corresponds to a logical unit e.g. * main code, subroutines, global variables, stack, heap. A logical address equals segment number, offset. 2.2. Address translation mechanism * each process has a segment table. Each entry stores base starting physical address of the segment, limit, length of the segment. Translation steps. 1. CPU generates segment _number, offset. 2. MMU retrieves base and limit from the segment table. 3. If offset is greater than or equal to, limit gives error invalid access. 4. Else gives physical address equals base plus offset. 2.3. Comparison. Paging versus segmentation criterion. Paging OS view. Segmentation programmer view. View OS, physical blocks programmer, logical blocks, size fixed pages, variable segments. Fragmentation, no external, internal possible, no internal. External possible transparency, transparent to programmer, visible to programmer. Protection at page level, stronger at logical unit level. Conclusion. We've explored two main solutions to non-contiguous memory allocation. Paging eliminates external fragmentation by using fixed-size blocks. With overhead reduced by TLB, segmentation provides a more logical program-oriented, but suffers from external fragmentation. In practice, paging dominates and has become the foundation of memory management in almost all operating systems: Windows, Linux, macOS, Android, iOS. On top of paging, engineers built one of the most powerful concepts in modern OS: virtual memory, which will be the focus of the next lesson. See you then.